We're going over notes for 8.7, L'Hopital's rule. So L'Hopital's rule says if the limit as x approaches a, many times it's either a real number or infinity, limit as x approaches a for f of x over g of x, if the result of this expression or this limit produces an indeterminate form of 0 over 0 or plus or minus infinity over infinity, then we can further evaluate this limit of this expression by taking the derivatives of the numerator and denominator separately. So limit of f of x over g of x, it's the same thing as evaluating the limit as x approaches a for f prime over g prime. And a lot of times this taking the derivatives for numerator and denominator will cause this expression to be a little bit easier to evaluate. But again, this only can be applied, this relationship can only be applied if we have indeterminate form of 0 over 0 or plus or minus infinity over infinity. Okay, so this rule works, but it has to be in this particular indeterminate form. There are other indeterminate forms, such as 0 to the 0 power, 1 to infinity, infinity minus infinity, 0 times infinity, or infinity to the 0. These all produce indeterminate answers, but if we want to apply L'Hopital's rule, we have to, and if we're sitting at one of these combinations of indeterminate forms, we have to convert these forms through algebraic methods to get it into this particular form before we can apply L'Hopital's rule. So the goal for a lot of these problems are how do we get from these indeterminate forms to indeterminate forms that are more useful, which will allow us to apply L'Hopital's rule. Okay, so we have to convert to 0 over 0 or infinity over infinity. So example 1, we have limit as x approaches infinity, e to the negative x times root x. So we can rewrite this maybe in the form that we can see to be more helpful, is if we convert the e to the negative x and move it to the denominator as e to the x in the denominator. So this, if we just rewrite this, we can think of this as infinity, limit as x approaches infinity of root x over e to the x. If I plug infinity into numerator or denominator, I'm going to get infinity over infinity, which is an appropriate indeterminate form for us to apply L'Hopital's rule. So now we can apply L'Hopital's rule. So separately, we're going to evaluate the derivative for the numerator. So root x, the same thing as x to the 1/2. If we find the derivative, it becomes 1/2 x to the negative 1/2. The derivative for e to the x is simply e to the x. And if we clean this up a little bit more, we get 1 over 2 root x e to the x. And if I evaluate the limit as x approaches infinity, we know that this denominator is going to grow to infinity. So 1 over infinity is essentially 0. So 0 is our limit. Hey, part B. Limit as x approaches 1 from the right side of 1. So we have a plus here. 1 over natural log of x minus 1 over x minus 1. And if we plug in 1.1 or 1.01, we're going to get infinity minus infinity, which is an indeterminate form that is not quite what we need, or what we need for L'Hopital's rule. So one thing that we can do is we can maybe rewrite this as one fraction. So maybe find common denominators. So common denominator will be natural log of x times x minus 1. If I balance the numerators, I'm going to get x minus 1 minus natural log of x. Once I have this as one fraction, I'm going to reevaluate the limit. So plug in 1.1, and I'm going to get, or if I plug in 1, I'm going to get 0. Numerator, I'm also going to get 0. So 0 over 0 is in the form of a useful indeterminate form. So now we can apply L'Hopital's rule. So we can evaluate the derivative for numerator and denominator separately. So x becomes 1, 1 goes 0, natural log of x goes to 1 over x. And then here, natural log of x times x minus 1, we have to go through the appropriate derivative method, which requires us to use product rule. So f prime g plus f g prime. So f prime is 1 over x times g, x minus 1, plus f g prime. And I evaluate the I found the derivative, but that's a little messy with all the complex fraction that we have. So if I multiply numerator and denominator by x, if I distribute the x through to every term in the numerator and denominator, then I've maintained balance in my expression and I haven't changed the overall value. So x times 1 is x times 1 over x is just leaves us with x. Denominator, distribute the x through, x's cancel out, I get x minus 1, and then I get plus x natural log of x. All right, so now let's see what happens if we plug in 1. If I plug in 1, I'm going to get 0 over 0 again, which means that if we keep getting 0 over 0 when we plug in our after applying L'Hopital's rule, we can continue going through L'Hopital's rule as long as we're double checking and making sure that each iteration of L'Hopital's rule we are testing and ensuring that we get 0 over 0 or infinity over infinity before we take a further step of L'Hopital's rule. But we've tested it and it is still in the correct indeterminate form, so we can continue with L'Hopital's rule. So x minus 1's derivative becomes 1, and the derivative for x minus 1 plus x natural log of x goes to 1, 1 goes to 0, and x ln x requires another procedure of product rule. So f prime g plus f g prime. Now if we plug 1 in again, I'll get 1 over, this goes 0, so 1 plus 1, so 1/2. Okay, example 2. We have limit of 1 plus 2 over x to the x as x approaches infinity. If I plug infinity in, I'm going to get 1 plus 2 over infinity, which is 0. So 1 plus 0 is 1, 1 raised to infinity. So 1 raised to infinity is an indeterminate form that we have to do a little bit more work on algebraically to convert this to somehow to be either one of these two forms before we can apply L'Hopital's rule. So one thing that we can do is when we have infinity or when we have a variable in an exponent, we can find a way to bring that down, but the way we can bring that down is we can use log properties. But if we want to do log properties, we have to apply natural log to both sides of the equation. So we'll take natural log of both sides. Natural log of, I'm going to rewrite this, equate this limit to equal to y. Okay, so I'll start off with this equation here. Y is equal to limit of my expression as x approaches infinity. So we'll take the natural log of both sides. Okay, and then now we can use the log power property. So this is nothing to do with derivatives yet. We're just going to bring this x down in front of the natural log to make our evaluation procedure a little bit easier, since it's difficult to work with a variable in the exponent. So we have that down. Now we want to try and convert this into a form that will help produce for us 0 over 0 or infinity over infinity. So I'm going to find a way to bring this x down to the denominator. So if I bring this x down to the denominator, I'm going to rewrite it as x to the negative 1. Okay, because I want to be able to move it to the denominator without changing the overall value. So if I bring this to the denominator, it'll have to become x to the negative 1. Now, if we evaluate this limit here, x approaches infinity, we know this will go to just 2 over x will go to 0, and natural log of 1 is therefore just 0. And 1 over infinity, or 1 over x to the negative 1 is the same thing as 1 over x. So 1 over infinity is the same thing as 0. So this form does produce 0 over 0, so we know we can apply L'Hopital's rule. So L'Hopital's rule tells us that we can separately find the derivative rules for numerator and denominator. So the rule for derivative of this numerator is natural log of u. So the derivative for natural log of u is u prime over u. So this portion's derivative becomes negative 2x to negative 2, since the 1 goes 0, and in denominator we keep it the same. And then the derivative for x to the negative 1, we go through power rule, bring down the negative 1, and then subtract 1 from the exponent. And if we clean this up a little bit more here, we can find that the numerator, the x to the negative 2 and this x to the negative 2 will cancel out. If I bring the negative 1 up, try and reduce this complex fraction, I get 2 over 1 plus 2 over x. Now if I evaluate the limit again, numerator will stay as 2, denominator infinity, and for this x, 2 over infinity is 0, 0 plus 1 is 1. So we know the value of this limit is equal to 2. Okay. All right, we haven't found the answer yet. We're trying to figure out what y is equal to, because y represents the limit as x approaches infinity. However, this 2 that we just found is now the right side, which is set equal to natural log of y. So we're almost there, but not quite. We now have to solve for y. Natural log of y is equal to 2, because that is the result of the limit of the right side of this equation. So if we convert this to exponential form, e to the natural log of y is equal to e squared. If I convert it to exponential form, it's e to the second power is equal to y, so therefore y is equal to e squared. Okay, part B. Notice that we have, anytime we're dealing with a limit and we have a variable raised to a variable, we know we have to involve natural logs to allow that x to come down. So we'll take we'll set this limit equal to y first, and then we'll take the natural log of both sides of that equation. We'll bring the x down in front, and this is not quite in the form of what we need for to produce something that we can use for L'Hopital. So we're going to again we'll find a way to bring that x down to the bottom. So when that comes down, it becomes x to the negative 1. So we get natural log of x over x to the negative 1. If I plug as we approach 0 from the right side of 0, natural log of x will go to negative infinity, and if I plug value close to 0, it'll also go to infinity. So negative over positive infinity is in the appropriate L'Hopital's form, where we can apply L'Hopital's rule. So we can now find the derivative of the numerator and separately find the derivative of the denominator. So natural log of x becomes 1 over x. X to negative 1 becomes negative 1x to negative 2. If we clean this up a little bit, we get 1 over x all over negative 1 over x squared. If we flip the denominator, it becomes negative x. And if I plug 0 in for this expression, I get 0. So 0 represents the right side of this equation. And then we want to figure out what y is. So we know that natural log of y is equal to 0. So convert this to exponential form. So e to the 0 is equal to y, and e to the 0 is 1. So therefore y is equal to 1. Okay, last one here. Limit as x approaches infinity for x to the 1 over x. Again, we have variable raised to the variable. We want to involve natural logs to bring this exponent down. So take the natural log of both sides, bring the 1 over x down in front, and then this x is already kind of in the denominator, so we can just rewrite it as natural log of x over x. Evaluate the limit, we get infinity, or limit of, natural log infinity is infinity over infinity, so it is in the form of that where we can apply L'Hopital's rule. So we find the derivative of the natural log of x, which is 1 over x. Derivative of x is 1, and then if we plug infinity in for this remaining x, this expression will go to 0. So then we want to solve for y, but right now we're at natural log of y is equal to 0. Convert to exponential form, so e to the 0 is equal to 1, and therefore y is equal to 1.